Okay, welcome back. Today we're doing lesson 9 in unit 4, integration of transcendental functions. So, looks like it got smudged there. Functions. Always fun. So take a moment here and kind of review some of these. I'll zoom out a little bit so you can see them all at once. But these are things that you should know, probably have it memorized, be able to use them. And just take a look at them, and then we'll put some of them into practice. So you might want to pause here, take a look. All right, hopefully you are back now. Let's do some examples of actually finding this integration. So here we have, let's go back down to number 1, the integral of 1 over x times the natural log of x cubed dx. Well, we're going to want to use u substitution again. We've done that before. So we're going to set u is equal to the natural log of x, okay? And then du is going to be equal to 1 over x dx. So in this case, x du is equal to dx, which is kind of nice. So I can rewrite this as the integral of x over x times u. Oh, and actually, I'm not going to write u cubed because it's not u cubed. It's 3 times u, right? Because this is ln of x cubed, so I should have actually put a 3 out there, times du. And you can see that these x's cancel out. So now I have 1/3. This is equal to 1/3 times the integral of u du over u, right? And the integral of du over u, you can see right up here, is equal to 1/3 times the natural log of u plus c, which in this case is equal to 1/3 times the natural log of x plus c. All right, kind of a fun problem. Here we have sine theta over 2 minus cosine theta. We're going to, again, have to use 2 sine, oh, you know what? I miswrote this. Let me fix this real quick. Okay, sorry. It's sine theta over 2 minus 3 cosine theta. I forgot to write that 3 there. So we're going to use u substitution again. Here I'm going to have u equal to 2 minus 3 cosine theta. So du is actually equal to 3 sine theta. So we can rewrite this as, well, du, oops, I forgot that d theta there. We can divide by 3, so I'm going to have 1/3 times the integral of 1 over u du, so it's actually du over u. This is the exact same thing. We're going to have 1/3 times the natural log of u plus c. Don't forget plus c. So that's 1/3 times the natural log of 2 minus 3 cosine theta. Oops, it's an absolute value. Plus c. Okay, all right. Let's do a few more here. Lots of examples again today. Cosine of t over 1 plus sine of t. Well, we're going to use u substitution. Keep doing that. We're going to use our u is equal to 1 plus sine of t. So du is equal to the cosine of t dt. And that's actually just the same thing here. So we have the integral of du over u. So that's equal to the natural log of u plus c, or the natural log of 1 plus sine t plus c. Okay, these might start getting a little repetitive, so let's switch it up and do some e's here. Nothing fun like e, right? Why did it get all fuzzy? Zoom in. There we go. X squared over e to the x cubed over 2. Quite a complicated thing. I'm going to set u equal to 1/2 x cubed. Okay, so du is equal to 3/2 x squared dx, right? So I can rewrite this as the integral of x squared dx I've got there, so I'm going to have 3/2 times e to the u times du. Okay, so that's equal to, oh, why did 3/2? Nope, it's not 3/2. Why? Why is it not 3/2? Because I wanted to isolate this, so I needed to divide by 3/2. So it should be 2/3. 2/3. So this is equal to 2/3 the integral of e to the u. If you go back and look here, integral of e to the u is just e to the u. Nice and convenient there. 2/3 e to the u plus c. So this is equal to 2/3 e to the x cubed over 2 plus c. Kind of interesting there. You know, we integrated something that looked pretty complicated, but it came out to be fairly simple and similar. Okay, so let's do another one. 0 to pi over 2. Well, look at this. Now we're actually dealing with a definite integral. We have 0 to pi over 2 of 1 minus sine x over x plus cosine x. What do you think you should be? I think you should be x plus cosine x, which is going to conveniently give us a derivative of 1 minus sine x dx. Okay, so this integral from 0 to 2, or 0 to pi over 2, and I can change that from 0 to pi over 2. I'm going to have 0 plus 1 to pi over 2 is going to be pi over 2, I believe, right? Yes? Good? Yeah, cosine of pi over 2 is 0. Okay, pi over 2 plus, got it. So this is going to give me the integral from 1 to pi over 2 of u du over u, which we're back to that natural log situation, right? So we have the natural log of u evaluated, not plus c, evaluated from 1 to pi over 2. So that's equal to the natural log of pi over 2 minus the natural log of 1, which of course is just 0. So this is equal to the natural log of pi over 2. Okay? I should have that in absolute values there. All right. 1 to 3 of e to the 2 minus x. Well, this one doesn't really have a lot, but we still should probably use u substitution just to make this simple. So u here is going to be equal to 2 minus x. So du is going to be equal to negative dx. That's important because if we didn't do this, oops, you can't even see. If we didn't do this, I think you would kind of miss that negative sign. So this is going to be equal to the negative integral of, and we're actually going to change our signs here too. So if we have 1, 2 minus 1 becomes 1. 2 minus 3 is negative 1. So we're going from 1 to negative 1, kind of interesting there, of e to the u du, right? So that negative sign came out here. So this is equal to negative e to the u evaluated from 1 to negative 1, which is equal to a negative 1 over e minus a negative e. So that's equal to e minus 1 over e. All right, perfect. Okay, let's do 4 more. Can you handle it? I think you can. We have the derivative, or the integral, excuse me, of dx over x squared plus 12x plus 37. Well, in this situation, we're not going to use u substitution because honestly, if we did that, we're not going to be able to eliminate anything. There's nothing good that will come of it. So here, we're going to complete the square. You can see that we have plus 37. We want to have something that's a little bit more simple to deal with. And this is where our trigonometry is going to come in, you'll see. So I'm going to rewrite this as the integral of dx over, and that x squared plus 12x plus 37, I want to be a perfect square, because if I have a perfect square, I can use some of my trigonometric functions here. You can see we've got perfect squares here in our denominators, and it looks like with that one, because we don't have a radical, we can probably use arctangent. We just have to be careful about it. So here, I'm going to rewrite this as, if I've got x squared plus 12x plus 37, I know that the square root of 36 is 6, and so 6 plus 6 is 12. So I'm going to have x plus 6 quantity squared plus 1, right? That makes sense. And I can actually now just integrate this as is. So here I've got an x value squared and an a value squared. So this is going to be equal to, you can see here, 1 over a. Well, our a is just 1, right? So we have 1 over a, and I'll do that, 1 over 1 times arctangent of u is this, right? Of x plus 6 over 1 plus c. And of course, to write that a little bit neater, we're just going to have the arctangent of x plus 6 plus c. And again, you can always write this as tangent inverse. That's the exact same thing, right? Okay, let's do another one of those since we didn't have a lot of experience with it. Here we have the derivative or the integral of dx over the square root of 4 minus 6x minus 9x squared. Well, I want to rewrite this as the integral of dx over, this is going to be a lot of information. I'm going to, let me pause for a second here and think. Okay, to be honest with you, I don't think this is a great example, and I kind of wish I hadn't done it, but I'm just going to do this weird algebra here, all right? So this is the same as the square root of 4 minus 9 times x squared plus 2/3 x plus 1/9, okay? So that's what happens if you multiply through plus 1. Ugh, such a huge mess. And now we can actually use some u substitution. Well, I'm going to rewrite this again as dx over the square root of 4, nope, not 4, 5, because 4 plus 1 is 5. 5 minus 3x plus 1 squared, okay? That, again, I just don't really want to dive into it. Hopefully you remember how to complete the square, but that's what's going on here. So u is equal to 3x plus 1, du is equal to 3 dx, right? And actually, just for reference here, a is equal to the square root of 5, okay? So this is going to be integrated here. We're actually going to come up with 1/3 times sine inverse or arc sine of, because we have a square root here, and this is our a, this is our x. We have sine, right? Sine, there we go, of 1/3, that comes from this, sine inverse of 3x plus 1 over the square root of 5 plus c, okay? Not a pretty problem, but you can kind of see a little bit, I think, how it works. So 2 more, and then we will be done. All right, 1 over 1 plus radical 2x dx. We're going to integrate it. U is equal to 1 plus radical 2x. U minus 1 is equal to radical 2x. Okay? Du is equal to 1 over the square root of 2x dx. So radical 2x du is equal to dx. Or u minus 1 du is equal to dx. What just happened there? Well, here we have u is equal to this. That makes sense to us. And then we're going to need this later, because when we find this derivative, it's still just not very helpful, right? So when we multiply this by radical 2x, then we can substitute in a u here, and that's going to make things easier to do. So I can write down here, this is equal to the integral of, well, du, we already know, whereas u minus 1 over u du, okay? Well, we can simplify that. So now we have the integral of 1 minus 1 over u du, right? That's even easier to integrate. So now once we integrate this, we've got u minus the natural log of u plus c. So now I can just substitute back in. I've got 1 plus radical 2x minus the natural log of 1 plus radical 2x plus c, okay? And the 1 and the c is a constant, it's any constant, so 1 just gets absorbed into that. So our final answer is just going to be the square root of 2x minus the natural log of 1 plus radical 2x plus c, okay? Let's do one more final problem. We have the integral from 0 to 4 of 5 over 3x plus 1. I'm going to have u is equal to 3x plus 1. So du is equal to 3 dx. So 1/3 du is equal to dx. Okay? If I change my integration here from 0 to 4, if I put in 0, I've got 1. If I put in 4, I've got 13. Okay? So this is going to be equal to the integral from 1 to 13 of 5 over, and I'm going to put this 3 here, 3u du. Okay? So that's equal to 5/3 times the integral of 1 to 13 of du over u. Oops. So we've got 5/3 times the natural log of u, evaluated from 1 to 13. So we have 5/3 times the natural log of 13 minus the natural log of 1. So we have 5/3 the natural log of 13. That equals 0. Okay, that was a lot of examples, and I think it went kind of fast, so hopefully all of that made sense. We'll do a lot together in class, and I look forward to seeing you. Questions in the comments, like and subscribe. I'll see you later. Bye!